SwayamPrabha. Digital India. Educated India.
Yes, in the morning, to summarize whatever we have been discussing, we started off with the whole electromagnetic spectrum and assigned certain regions to certain molecular motions. We said the region from ultraviolet to visible, whole of it is for electronic transitions. Then after that, near to mid-infrared region is useful for studying the molecular vibrations. Then for the microwave, we said it is going to be very useful for studying the rotational motions in molecules. Right? And then we particularly talked about electronic excitations. So we started off with UV and then visible radiations, how electronic transitions would happen in an atom, how that's going to be different in molecules, right? So all of this we discussed. And then we started off with a very simple system such as ethylene, and then slowly started adding the conjugation, right? We built the conjugation. We said upon addition of 11 double bonds in carotene, you can push the absorption to the visible region. And then we also talked about some aromatic systems by appropriately putting the substituents, donors and acceptors, or electron donating groups and electron withdrawing groups. You will be able to push the absorption to the visible region. Even for a simple system, you should be able to do it, right? And then we took few systems. We looked at benzene, we looked at thiophene, or heteroaromatics in general. And then we talked about the aromatic stabilization differences, how a lower aromatic stabilization energy would be helpful for it to dearomatize it very readily, right? Such systems could in principle be used as switches, right? So if you could destroy it, extend the conjugation, it becomes colored because it loses aromaticity, which it doesn't want to. So it would come back quickly to the colorless state, natural state, which is aromatic. So that's a driving force that is built in. Then we were discussing about few systems, and we started off with a few model compounds for photochromic systems with a definition at the very beginning. Then we said in all these cases, most often you will come across an electrocyclization reaction where only electrons are involved, no bond breaking and bond making. And there are a set of rules that these electrocyclization reactions, which fall under the category of pericyclic reactions, obey, and that was given by Woodward and Hoffman, right? And we took a particular example, cyclohexatriene and butadiene. We discussed how these orbital signs are very important in establishing a bond, right? And the reverse reaction of breaking the bond, right? So how that is going to dictate the course of a reaction under a particular condition. This is what we discussed. It's very quick summary of the whole big area of pericyclic reactions, okay? So then right now we were discussing about this particular example where in the beginning you had two benzenes connected via a alkene, a olefin, a carbon-carbon double bond. This molecule's name is, any of you are aware about this? How do you call this? Diphenyl ethene. Yeah, you can call that 1,2-diphenyl ethene. Okay. Another common name for this is stilbene. Okay. Geometry wise, if you look at stilbene, S-T-I-L-B-E-N-E. Okay. Stilbene, yeah. So this is in, what is the geometry of this? Cis or trans? Cis, right? When you shine light onto such cis isomers, what is the fate of this molecule? If you look at in the excited state, this double bond character for the middle olefinic part is lost. Okay, so you actually, to start with, it has an sp2 hybridized carbons. All the other carbons are also sp2 hybridized, but the central ones have two carbons and they are sp2 hybridized as well. In the excited state, which one would be easy to be removed? The one in the olefinic or in the benzene? One in the olefin. Pi stars available. Quickly you can excite an electron and pi to pi star transition occurs, and because of that you will lose the sp2 hybridization nature for these carbons, they would become an sp3 hybridized carbon, having one of the lobes carrying one electron. So what does it mean? It is a radical now, right? Both the carbons acquire a radical characteristic. So they become sp3. Once it becomes sp3, they have a free rotation that it can undergo, right? This sp3 hybridized carbons. Look at this portion. Now this has become sp3 hybridized. This phenyl ring can rotate. So you start with the cis isomer. What do you end up with? Only trans? You get a mixture of products. You get cis, you also end up in trans. Okay. If you start with trans, what do you get then? Again, you will get the mixture of cis and trans. Their compositions that are arising from the same excited state is going to be same. The composition of the cis and trans in the mixture that has evolved from the excited state, be it cis or trans, right, is going to be having a same composition. Composition could be 60-30, means if you start with trans also, you will end up in getting 60-30. Such a state is called a photostationary state, PSS, okay, photostationary state, yeah. It depends on the wavelength you choose for excitation, okay, and the molar extinction coefficient of a particular compound at that wavelength, okay. Exactly. More number of photons are absorbed. It's going, for example, you have cis stopping at 350 nanometers. Trans extends up to 380 nanometers. You choose the trans region alone and start pumping light, and more of cis you can populate, because that is the region in the mixture cis doesn't absorb now, because you are exciting at the trans. Okay. So this is where you can slightly modify or improve one isomer over the other. Well, this is one possibility that is shown here. Of course, you will have a mixture of this because they are in equilibrium from the excited state, right? Another possibility is the electrocyclization possibility, right? If you watch carefully, you'll see these two carbons, one pi bond of the benzene would undergo like a cyclohexatriene. They would, right? The terminal lobes would overlap to form a constructive interference, establishing a bonding scenario, and you construct a bond there. Now, what has ultimately resulted because of this is you have destroyed the aromaticity of those two rings. Is it not? This ring, this phenyl ring has lost its aromaticity. The other phenyl ring has also lost its aromaticity. So the species that you have generated is going to be a high energy species and not certainly going to be stable. And hence what it does, it goes back to the stable state, which is cis or trans, by acquiring the aromaticity. So it regains the aromaticity. So this process is very fast. Okay, it is a non-aromatic. It is a dihydrophenanthrin. Phenanthrin means you established an aromatic one. The final one that you are seeing is phenanthrin. Somebody in the morning they were mentioning about phenanthrin. So that is the angular analog of anthracene, phenanthrin. You can get to phenanthrin, right? And you can prove that it goes via this DHP intermediate only, which is dihydrophenanthrin intermediate. How do you do that? In the photochemical reaction, you add a little bit of oxidant such as iodine or purge oxygen, whatever, or purge air, right? It's going to oxidize the intermediate by resulting in aromatic compound, which is phenanthrin. Once that is generated, you are not going to revert the reaction to the precursor, because it is a stable compound. Once it is generated, it's going to be there. Okay. So this is an unidirectional reaction, but this is an equilibrium reaction. This is also an equilibrium reaction. So if you start off with the phenyl, 1,2-diphenyl ethene, okay, you are not going to see a photochromic scenario. The intermediate that you are going to generate is going to be very short-lived, even at -100 degrees centigrade. Okay, it would rapidly go back to the aromatic system. So photochromism is not observable for such compound. So how do you overcome this barrier? Then they thought of introducing thiophenes into the system, because thiophenes have lesser aromatic stabilization energy when compared to that of benzene. So it is not highly energetic. You can easily destroy the aromaticity. By that way, it doesn't feel a big difference with aromatic and without aromatic. Even if it loses the aromaticity, there's not much of a difference that it's going to lose. So with that compromise, they've started off with thiophenes. But thiophenes, as you look at, it's carefully engineered. Okay, you look at that there is an ethylene unit same as this, and you also see the alkyl group substituted on either sides, right? And you also have alkyl group substituted on the other side of thiophene, and they both are connected via the olefin. So if you take this as a starting material and then shine light, what all the possibilities that you can expect? Just compare this compound with the previous scheme that is shown there. Can you predict what are all the possibilities?
Sir, does the center, center, is that a ring, closed ring, or are there two substituents in the substituents?
This one, these are substituents. They are overlapping like this. No, that's not the reason. You first tell me what are the possibilities for this system by comparing to the top scheme.
So,
what are all the possibilities? We talked about few possibilities there. What are all the possibilities for this compound now? When it cyclizes, if you think of cyclization, obviously here also aromaticity will be disturbed. Is that possible in this system? It was possible here. Is it possible in this system? No. You wanted to ask something?
Is it possible to remove the substance and form a double bond over there?
Where? Here?
Over
Like
there,
here?
yeah.
Huh?
Yeah.
Here?
To complete the ring.
Here?
Yeah, exactly.
Why do we want to do
not the
that?
sulfur.
We need only 6 pi electrons to undergo electrocyclization, and that's already there. 2 are there, I mean 1 pi bond is there, 2 pi electrons are there in this thiophene, 2 pi electrons are there in this thiophene, 2 pi electrons are there here. So 6 pi electrons are fulfilled. It can undergo electrocyclization as such. So one possibility that he mentioned was isomerization. You will see for this compound also, right? Another possibility is it can undergo electrocyclization, as I mentioned now. So it can undergo electrocyclization because it has 6 pi electrons. What is the another possibility that is arrested in this system when compared to that one is that the loss of hydrogens to give you an aromatic system is not possible here because hydrogens are replaced by methyls, substituents. Now there is no way that it can lose the hydrogens and form a stable aromatic product at the end. So the other competing step just in presence of air is ruled out. Yeah.
sir, why can't the methyls themselves lose a hydrogen each and then bond with each other? The methyls, the substituent methyls.
Methyl, see, anywhere you want to see say, hydrogen abstraction or something, they must be in a closer proximity. These methyls, when you look at, I'll show you the crystal structure of this. One of the thiophenes will be like this. Let's say this is the alkene plane, and the thiophene units are attached here. They are not flat like this because methyls are bumping in, right? So one of the thiophene will be away from plane, and this thiophene will also be away from plane. Actually, when you look at it like this, you will see these methyls are hitting each other. But the way that they have organized themselves is pointing one methyl above the plane, another methyl pointing below the plane. That's how you would see them. Okay, so they are not very close between themselves, they will not undergo any kind of reaction. So the main purpose of putting this methyl is not to generate the oxidized product. So one step is prevented now. You have to now carefully watch the engineering approach, how scientists have worked on developing a stable system, right? And how they can make it reversible. So that is the message you need to get here. So here, electrocyclization is a possibility, isomerization alone is a possibility. So there are two possibilities. Then a strategy evolved, okay, to from an sp2 hybridized carbon cleaving, carbon-carbon bond cleavage is not that straightforward by photochemical methods. Okay, the bond dissociation energies are significantly high, right? So, like I said, if you have to cleave, then which is the wavelength that you should be using? Oh, far ultraviolet radiation or vacuum ultraviolet radiation. To that extent, you may have to go. Only then you will be able to cleave. But here, people use the wavelengths that are far from such, harmful radiations to observe the property. Yeah.
So would it be possible to bring the double bond outside and like try to form a more like a longer chain resonance? Like
this double bond.
Yeah, one of the double. No, not that one. The
this
one.
In
the
these double bonds.
Yeah, the sulfur. Yeah, inside.
Attempts have been done. You are right. Your guess is correct. Yeah. If you do so, after cyclization, you can create a more extended conjugation. Yeah. People have done that. I am talking about a story which has evolved 20, 30 years ago. Okay. So, from the basic skeleton, how they would build to achieve to a much better system. So, in the following examples, you will see many of them, and you will see each one exhibit a characteristic absorption and a reversibility tendency. Okay. So, now the objective is how to arrest isomerization. Isomerization is a competing factor. If you arrest that, then you will promote only the electrocyclization and you will be able to shuttle them between the colored state and the colorless state. Okay. So, now how about locking the double bond? Okay, that is the next idea. They wanted to arrest isomerization. If there is not locked this way, then it has a possibility to achieve trans. Now you put them in the same geometry, cis, the same side of the double bond. So you should be able to lock them on the other side, right? When you lock this, you will not be able to have cis to trans isomerization possible, and these arrays are in a closer proximity, right? In a distance of forming a carbon-carbon double bond, carbon-carbon single bond. Sorry. So now, instead of this phenyl, they started varying thiophene, furan, pyrrole, all of this system, incorporating a lock at the top of the double bond. Okay, the lock which involves the double bond. Yeah.
So how do you lock the double bond?
There are certain functional groups, as you see cyclobutene here, you see cyclopentene, cyclohexene. You just form a cyclic system, make the double bond part of a cyclic system. Okay. Okay. And then it is arrested. So isomerization is not possible. For isomerization, these bonds should, from this way, says it has to come to 180 degrees. Right. Now, once you lock this, it can't come to 180 degrees, not possible. It will be only in this way. Okay. They are locked up. So this is anhydride unit. Cyclobutene, cyclopentene, and cyclohexene. Don't be worried about the substituents there. Yes, that's nothing to do with the color that you generate, but it is about the processing capability with systems. Okay, how do you process? How the solubility is and so on. Yeah.
Sir, why are we trying to reduce the number of possible structures of this compound when it just reacts with light? I thought we were supposed to increase the conjugation so that it can display this kind of effect. Why are we?
That's right, but first you need to arrest the other competing possibilities. So first we initially arrested the oxidation possibility. Then we started arresting the isomerization possibility. Now, because these two possibilities are gone, it should only undergo electrocyclization. There is the only possibility left. Then, once you accomplish that, you start to achieve the extension in conjugation, whatever, and then play with the color. All the things to be done. So, this was the first effort in locking and achieving only electrocyclization.
Sir, so these will work only with specific structural geometrical isomers. It won't this
common
photochromosome. So could we see here we are using all cis isomers? If we had used trans isomer, would there be a way to engineer it so that we would get a we would get that photochromosome effect?
trans cannot be locked, you have to convert it to a cis, right? Then you use it to lock. The way people plan the synthesis, you're talking about synthesis, I suppose. I have not shown any slides on synthesis. They take this precursor, okay, which is properly substituted on either sides, and then take this as a monomeric unit and then attach it onto this linkers. That is the way, right? They don't start with an alkene. It's quite challenging because you need to start with the trans, means you need to isomerize to cis, then you need to have the appropriate functionality on the double bond of this, olefin diaryl ethenes. Then you have to lock them up, right? Instead, you have a locked system already, which is appropriately functionalized. Let's say you have a halogen on these two ends, which is easy to make, right? Now, you have this unit with an appropriate functionality, which can couple onto the halogen, form a carbon-carbon bond. Transition metal catalyzed reactions are very popular. Some of the lectures, I know that you have heard, right? Transition metal catalyzed carbon-carbon coupling reactions. Very popular. Nobel Prize has gone to that. So, you can establish a carbon-carbon single bond very easily. Any heteroaromatics you think of, they are available with such modifications. You just buy them or you can make them conveniently in the laboratory and then couple them, right? So, that is a very established method. It's very easy also, good yielding synthesis. So, one can approach that method. Now, among these systems, people have figured out that the cyclopentene unit keeps these aryl rings at a very right distance, and if you think of stability, they are good, planarity wise also perfect, and one can do electrocyclization reactions very convenient. Okay, so for stability wise also fine, planarity wise also cyclopentene stands high. Okay, so that is a common unit you will see, and as he asked, various pi extensions have happened. You can benzanulate onto thiophene, you can fuse a benzene, you can also attach the benzene unit. Likewise, various modifications have been tried, and people have tried to understand what kind of colors they would generate, how they would modify their optical properties or absorption properties. All of that could be done. So, you start off with these compounds, they all look like colorless solutions. Moment you shine light on them, they change to the corresponding color. Switch off the light, they would go back from colored state to a colorless state, which is very transparent. Okay, so this back and forth they can do multiple times, mainly because you construct a carbon-carbon bond via electrocyclization. Aromaticity disturbed, and moment you switch off light, the carbon-carbon bond newly generated is cleaved, once again allowing it to regain the aromaticity. Okay, so this is the forward and the backward processes that is happening during photochromic behavior. Now, this is all in solution state. You may be asking, sir, if I crystallize this compound, it's in a solid state, will you see such color changes, reversible color changes? That has also been examined. What you will see is, okay, so this is just a picture to tell you that these molecules have applications in photochromic lenses. Okay, so start from a colorless state, forms a gray color, and switch off the light, or then it comes back to color. This is the example that I was mentioning. In solid state, these molecules undergo photochromic behavior. They exhibit photochromic behavior again through the same process. It undergoes a 6-pi electrocyclization, establishing a carbon-carbon bond. On the other hand, both these aromatic rings loses aromaticity in this process. The moment you switch off light, they would fade away, coming back to the natural state. This is very, very important, and it will allow you to think. In a solid state, you must have studied these, right? Motions in the molecules are there or not? They are negligible. So, you call them as restricted molecular motions in the solid state. You cannot say there are no motions. There are motions, but the motions are restricted. So, geometrical changes can happen, because you are changing an sp2 hybridized carbon during electrocyclization to an sp3 hybridized carbons. 2 sp3 hybridized carbons are being constructed in that process. So, hybridization changes, right? So, from a flat planar sp2 to a sp3, with a bond angle of 109.8 or whatever, that is being achieved. So, small deviations in the structural changes are possible in a confined environment also, and that is responsible for this color changes in the solid state. Okay, people have trapped it because it will fade away quickly, right? So, you freeze them, take it to low temperatures and trap this intermediate that is generated, the photochromic intermediate, which is responsible for the color. They solve the crystal structure, they find there is a carbon-carbon double bond that is, carbon-carbon single bond that is established during the electrocyclization process, okay, when they gain color. And they have also detected how much of structural changes that happens in the solid state. I think I have that slide. Yeah, see. Next slide is that. So, for example, this compound, when you dissolve them in solution, you see initial state 4A gives you absorption only till 350 nanometers. Right, turn on the wavelength where it has absorbed. So, you pump in radiation of 300 or whatever, or 325, right, wherever it has an absorption. If you shine light with that, then it is going to absorb the light, undergoes the electrocyclization, establishes a conjugation, and now the absorption is completely different from that of the 4A previous compound to start with, right. So, now it is completely different. You have a new band appearing at 500 nanometers. So, certainly it has established an extended conjugation during photoexcitation. So, now they have compared the crystal structures of the ring open isomer and the ring closed isomer. The changes are quite evident. Start from a ring opened isomer. If you measure from the sulfur edge to the top of the 5-membered ring that they are using to lock it, see the distance is about 0.49 nanometers to start with, and the molecular width, if you compare, it is 1.01, right. Shine light, ring closure happens. Now you cool it, trap the intermediate, crystallize it in a solvent. Then you study the crystal structure. In the solid state, you find that there is a expansion. You see that from 0.49 to 0.56 nanometers. And the width of the molecule has also decreased, right, from 1.01 nanometers to 90 nanometers. These measurements, they are very powerful microscope. Okay, when you mount the crystal itself on the diffractometer, you will be able to see if there is any small changes associated with the crystal shape or size or whatever, right. But when you are solving the structure, once you have solved the crystal structure, you can take the data, solve the data, you get such structures, put it in a program through which you can measure these dimensions. It will help you to, for example, mercury, it is a freely downloadable software. You can also try taking a solved data of a X-ray structure, put it into this software, just you can rotate and see how these molecules are, what are the bond lengths are, all of them you should be able to measure. Okay, such dimensions are very accurate from the solid state structures. So, now this is a view from the top, right. I want you to look at like this, the molecule. So, now this is flattened. You see, as I described, these thiophene rings are not flat. One is pointing upwards, another one is pointing downwards. You see the methyl, one is pointing upwards, the methyl is pointing downwards. Where is that double bond, wolfenic double bond? That is at the center. That is considered as a plane, right. So, to that plane, these thiophene rings are tilted, correct. What it means, you can also look at it in a different perspective. Let us say these orbitals are located on this, on the edge of this thiophene carbons, because this is the place where it is going to establish a carbon-carbon bond after electrocyclization, and these orbitals are perfectly aligned. Okay, from this carbon will have the lobes like this, another carbon which is below the plane will have lobes like this, right. So, this end is positive, means this end is going to be positive, they will have a very nice interaction between them. So, due to this proper arrangement of the aryl rings or the heteroaryl rings, the bond is established. Once the bond is established, you will see the structure becomes more flat than it was before, right. So, such a small structural changes impact the packing in the solid state, how the molecules are organized. So this is a very small information. People have used these structural changes in solid state and they have made the molecule to work. Okay, it has done some work also. I'll show you. Little old report, but very exciting study. Right, a group from Japan has done this, and their question was, can a small molecular shape change in the solid state lead to a very bulk motion? That was the question they asked. So for that, they took a simple sample such as diaryl ethene, they crystallized it, they could grow needles of dimensions what is shown there, about 200 micrometers or so, and these crystals are like this, right? When you shine light, the tip of the crystal bends. The tip displacement is of certain few micrometers. Okay, so a crystal is bent now. When you stop shining light, it comes back to its natural position, and the author proudly calls this as a crystal tennis rackets. Okay, so this is like the bat moving against the ball and then hitting it. So it looks something similar to that. So he has called it as crystal tennis rackets. Now this bending phenomena is noticed, right? So you have a needle, you shine at the tip. So there is some molecular organization happening in the crystal, and because of that, if one molecule gets reorganized, the next molecule also reorganizes. In a solid state, you have perfect arrangement of molecules in a three-dimensional fashion, right? So if one initiates a reaction, the available space is compensated or used by the next molecule, and again the available space created is used by the third molecule, and so on and so forth. So it is a complementary effect, or you would say a sequential effect from one to the next and then to the next and so on and so forth. So this is a very cooperative effect from the beginning till end, and because of that, this small changes would allow the crystal to bend. Okay, this was their rationalization, and they've done very careful studies. It's very difficult to do. As I said, powerful microscopes are necessary, diffractometers at lower temperatures one should be able to do. All those facilities are there, one could do. So it's a simple molecule. As we saw in the previous example, they have extended the conjugation with phenyl on either sides of the thiophene. Now this crystal, if you look at, this is in square shape. You can draw the crystals of them. They are in square shape. Okay. Moment you shine light, there's a small change in the shape from square to lozenge. The color also changes, right? So that must have been because of the electrocyclization and then, CC bond formation, sp2 becoming sp3 and all that effect. So there is a small structural changes, and they have measured all the dimensions, corner angle decrease and all that. So fine. This is not for one sample. This for another sample also. So what it means is, it's not a serendipitous result. It is happening in every molecule in the solid state. So in solid state, motions do happen, supplements it, photochromic behavior happens, and you are able to see that in every crystal. So one more crystal is also built, and that is a rectangular crystal. Again, this rectangular crystal undergoes an expansion and contraction, which was measured very carefully, and they could identify the expansion and contraction by 7%. If somebody is reporting a 7% expansion in a crystal, just to look at the accuracy that they deal with. Okay, one should be able to appreciate, one should be able to design an experiment to that level. That perfection is necessary in science, right? So crystal length also, they have figured out that it proportionately decreases up to 7% and so on. But the crystal changes to color, and it once again is reversible, which is shown in the absorption spectrum, and they have studied the absorption maximum at a particular wavelength, how many times fading comes back, and all of that with respect to a particular wavelength is measured, right? So now that initial needle was taken, which was undergoing a bend, right? It was bending upon photolysis, and they've done repeated cycles up to 80 cycles. Shining light, switching off, shining light, switching off. Every time it bends to the same distance, so the tip displacement is found to be about 48 micrometers or so, right? Every time you shine light, the tip bends to about 48 micrometers, comes back. Not only one time, they've done this experiment multiple times up to the 80th time. they could measure, and there is no change in the tip displacement, highly reproducible. Okay. Now, having excited by those results, these authors went further, beyond. So they, yeah, please.
Sir, so in this case, you said that the crystal is bending towards the light source. So that means the light is shining on only part of the crystal. It's not shining on the whole crystal.
No.
Only on part of the crystal.
Yeah. So it is kind of a laser beam which just points at a particular part of the crystal.
Sir, what if you shown the light on the full part of the crystal?
More of it would bend. Now only the tip displacement is what they have calculated. So if you can grow a longer portion of the crystal, it's 200 micrometers. So if you go even more longer, if you can do that, then majority of it you will see that bending. So the longer portion would bend instead.
Sir, then why won't the last part bend?
But
I
don't know, maybe that's not exposed, right? Because you're fixing it onto a holder, right? The other tip of it is rested on a holder, or it is just fixed to a holder against which you shine light now. So one end is available for it to, you can expose it to light, but the other end is already buried. You are not using the whole crystal to expose to light. That is what is their method of the light, because that what they have given a proposal that the first molecule that faces the light is going to initiate this sequence of processes that is happening afterwards, and they are all happening in a cooperative manner, and that results in an overall bending of the crystal. Okay, so it's a cumulative effect. Well, you see it as a bending. Okay, fine. So now this bending, because this does a movement, okay, can we have a nanoparticle at the tip of the crystal and allow it to push it? Right? It's like a hockey bat. You have a ball, and then you fix one end of it, and then shine light is going to push the ball, comes back, push the ball, comes back. So similar situation they could imagine. They had used a gold microparticle of this much size, roughly I would say somewhere 70 micrometers or 60 micrometers or so. That is the size of the gold microparticle. They placed it at the tip. Now again another end of the tip is fixed at a point, shine light onto the tip. It's going to bend now, pushes the gold microparticle to a distance of about 30 micrometers. Initially it was roughly about 60 micrometers, right? How much did we see in the tip displacement? Yeah, 45 micrometers. Now it has come down to 30 micrometers because you loaded it with the gold nanoparticle, right? So it's facing some difficulty to push it, not to that much extent, but it is okay. It does some job. So made a molecule to do a job. So it is able to push the gold microparticle to a distance of about 30 micrometers. This is a very simple demonstration how a molecule could be put to use, right? So in a very miniature or in a tiny device, you want to put in a molecule and then allow it to do some function. Such kind of small scale functions one can think of. Okay, so this is a nice demonstration. It was published in Nature actually. The whole report, it's a very, very cited, highly influential paper, I would say. So they have proposed like this for the same question that you asked. So they call it as an artificial muscle because you see in one case that swelling of the crystal happened, right? It has expanded. There was also a contraction. So it is like our muscles, right? Bulging and then shrinking. So similar kind of an aspect you can expect in crystals. So they call it as artificial molecular muscles. Okay. So do we stop or stop, right? You have any questions you can ask, and few clarifications in the morning, right? You the absorption, it is I0 by I, log I0 by I. It was in two places it was represented wrongly, and it is going to be a transmittance, means then it is going to be I by I0 because it is transmittance is inversely proportional to absorbance, right? So the notations are different in two places, but it's for the same absorbance, so which is an error. So you may have to correct it. And some of you were asking about black color, right? So if you see an object black means it has absorbed all the colors, that you must know. Okay, it has absorbed all the colors. So if you take a carbon black or any carbon, record the absorption spectrum, you will see it is taking up whole of the visible radiation, right? So which means it absorbs all the wavelengths, right? Then it it is appearing as a black to our eyes. And white, somebody was asking about white, right? White means it doesn't absorb any color. That means what? It doesn't absorb any visible radiation. Visible radiation only you have the colors, right? So it doesn't absorb any of that. So the object appears white. That means if it is colorless, we know that it's going to absorb the ultraviolet radiation, right? So which means it doesn't absorb any visible radiation. So it is fine. Yeah.
So my question is, white light does, if the object appears white, it doesn't absorb any colors. So what's the difference between white and transparent? Transparent objects also don't absorb any light.
Yeah.
So what's the difference there?
Transparent is again colorless only, right? So it will absorb ultraviolet radiation, not any colors, not any visible region colors. Okay. So the wavelength is going to be absorbed in the ultraviolet. Absorption happens for that too, but it is not the visible region wavelength. It is a wavelength that is at a higher energy. So, and another question was asked by the other student, I think, when we were talking about the different colors, natural colors and its absorption. He was asking about Geese 531 or something, 631, some numbers he was pointing it out. That is a dwarf planet I read. I was not aware about that. So, that is a dwarf planet whose color is red. So, the region is connected to the color of the dwarf planet. Okay. So, that is a red region close to 630 or somewhere you would have noticed that, and this is connected to the dwarf planet. Another region was written as sun, meaning that in the solar spectrum when you look at, this is the major absorption you would have, that region from 450 to 550 or so. That is the major portion where the solar spectrum has absorption. If you look at the solar spectrum, very minimal or average at the ultraviolet region. But from the region of 450 to 550 or so, you will have the maximum absorption for the solar radiation. So that is the point. The region was nicely depicted. Yeah.
So we were discussing about the solid state, and over there, like for example, if we see red, the crystal is appearing red, it implies that it has absorbed the bluish green radiations, and what we see is red.
Right.
So that is not concerned with the emitted light.
No.
It's only concerned with the absorption.
Yeah, it is only the absorption. Yeah.
If a sample is experiencing a UV radiations and also visible light radiation, and if the sample absorbs the UV radiation, then it will emit all the visible radiation.
Maybe, yeah. Because it should be appearing at a lower wavelength, so there are chances that you may end up in getting the emission at the visible region. Okay.
So it must emit white light. It
For
must
what?
not be transparent.
No, emission, if it is appearing in the ultraviolet region, you will see a violet emission of the sample. It will give out violet light.
The mixture of all the visible light is white.
A mixture of all the visible light is white. That is true. Emission will be white in that case.
Not transparent.
No, not transparent. It will be white. Yeah. Okay, so I have brought some. Yeah, please.
So I'm just confirming whether what I understood is right. So we take the molecule which we have engineered and it absorbs the normal absorption spectra is some UV radiation which is before the visible spectrum.
Okay.
So therefore it looks colorless. So what we do is we increase shine that that particular frequency of UV radiation. The structure changes, and then whatever other light is coming, it absorbs some part of that and gives it a color.
Other part of it, colorless sample absorbs wavelength in the ultraviolet region.
Yes, sir. So when we are changing the structure, when we are doing the electrocyclization, we are
That is initiated by irradiation.
So we are only giving that particular frequency.
Yeah.
And then after that, we are giving all the other frequencies.
You are giving particular frequency where the molecule is absorbing.
Yeah.
Such that the molecule can absorb light and it can undergo this process.
So then that we are not providing that other light for it to absorb. That is just coming from the environment.
No. If you are not supplying the other wavelength, let me go back to the spectrum. right? This is where you are shining the light for the ring open form. Absorbs the light, forms that product whose absorption looks like this. Now,
So we are providing the light for that also.
you can. Otherwise also, if you don't supply, reverse process is thermally favored. Comes back to the colorless state. If you want to use light for the reverse process, you should shine light where the newly generated species is absorbing. You understand? Whose absorption is not overlapping with this, not in this region. You have to choose this region, right? Then this newly generated species absorbs the light. It would go back to the colorless state. You will see that this band is decreasing with time and slowly it will appear like this. Okay, so you can do time dependent studies on it for the evolution of the new species and for fading of the new species. Both of them one can try. Yeah.
Sir, if there's like a enough extended conjugated system, can it also absorb in like the infrared region?
In principle, yes. If you extend the conjugation and push the absorption to the infrared radiation, it should absorb in the infrared radiation.
So like, is there any example of it? Or?
There are. The examples are very useful in the sense of bioimaging aspects, because the chromophores that are in our body system, right, they can absorb the visible light and ultraviolet light, but they are transparent to infrared radiation. At least our skins are transparent up to 1 centimeter depth. They are transparent to infrared radiation. So that's why this radiation therapy based, cancer treatment, all of them works like that. So you shine in infrared radiation, put the dye inside, you will be able to, you can pass infrared radiation and that dye would do its job. Right? It can deliver a drug at the particular place, or you will be able to image them. All of that is possible only with infrared, the dyes that can absorb in the infrared region. That's why the porphyrin systems that are in chlorophylls, you have this ring system, right? Tetrapyrrole ring system. Those are very, very much helpful, because they can, by extending the conjugation, they can absorb in the infrared region. Such dyes are very much used. Okay, I don't know whether you are familiar about photodynamic therapy. You can go through it. I mean, that mainly targets this infrared radiation. Okay, good. Okay, so I stop here.